Thank you to ICSESS21 for inviting me to deliver this talk, Enabling Organic Waste Conversion to Soil Enhancer for Sustainable Agriculture and Food Productions. This talk is in line with the theme Promoting Innovative and Multidisciplinary Research in the New Norm. My name is Chu-Tin Lee from the School of Chemical and Energy Engineering. Waste management is a complex issue faced by many countries. It requires a paradigm shift when we move into the 21st century. Ideally, the waste sent to the landfill could be minimized, where more viable technologies could be introduced to convert waste to value-added product. Ideally, all landfill sites should be built as a sanitary ones to facilitate the collections of leachate, to facilitate treatments and avoid underground water contamination. However, most of the landfill sites in the developing countries are operated as open dumps where leachate is released to the underground water, causing further pollutions. Typically, sanitary landfill is quite costly in terms of capital costs as well as for the maintenance. According to the What a Waste 2.0 report prepared by World Bank Group, indicating that world waste is expected to rise to 3.4 billion ton by the year 2050 if there's no paradigm shift in terms of the way we treat waste. From the compositions, it shows that up to 44% consists of food waste. As you can see from this pie chart, the global waste treatment methods is still relying largely on landfill, where other technologies such as recycling, incineration, or composting are still at a smaller percentage due to higher costs. Looking at the waste management costs, it is not just about the treatment costs, it also covers collections, transportations, and also the final disposal. The cost can range from about $35 per ton in the low-income country to up to $100 per ton in the higher income countries. This is because about half of these costs are caused by the labor and transportation costs. However, if we look at the user fees, meaning how much of consumer or household have to pay to cover this cost, it is only about 35 to 170 USD per year for low income and or high income countries respectively. This is because most of the cost is still subsidized by the government, or in other words, actually taxpayers are paying this cost. Towards zero waste, how realistic is this goal? If we look at how waste can be segregated, for example, paper, plastic, e-waste, and we consider it as recyclable or dry waste. These are the waste that can be stored at a specific location, for example, at home or in a residential area for a relatively longer time. However, for food waste, it will demand higher frequency of collections, otherwise it will cause odor emissions and also pest problem. In other words, there's a higher urgency to valorize food waste in a more efficient manner in order to achieve overall efficiency for resource recycling towards zero waste. This is an ideal scenario showing how bio-waste can be recycled to support circular economy. For example, organic waste from the restaurant or food industry could be converted to compost, and the product can be used to fertilize the vegetable farm or landscape to further promote the productions of the crop and meat. Similarly, the organic waste can also be used to generate biogas or animal feed, and this can form a symbiotic network supporting circular economy. Let us first look at how composting can be a viable technology to valorize food waste. In many countries, waste segregation as source is being introduced. For example, in China, mandatory waste segregation was implemented in Shanghai in July 2019. This will involve training and outreach with the citizens to guide them on how to segregate the waste correctly. It is then the segregated waste will then be transferred to the transfer stations before they are pulled and sent to the further treatment center. Ideally, there could be facility such as MRF, material recycling facility, to further segregate those dry waste for recycling purposes. As for the wet waste, such as mainly the food waste, could be further treated, typically through composting and anaerobic digestion. The liquid portion, or we sometimes call it as leachate from composting, and the digested from anaerobic digestion can also be further formulated as a liquid fertilizer. So both the compost and the liquid can be used as a fertilizer to fertilize the agriculture land. Considering the closing the loop solutions, making composting as a more viable technology will require systemic solutions in which it will involve multiple stakeholders to make it to happen. For example, from the top-down exercise, it will rely on the proactive actions by the government and local government, to private sectors on how the value propositions of converting food waste to compost could be invested by the private sectors or corporates. This will also require the behavior change of the bottom-up approach by the community in terms of participations, proper waste segregation, and so on. So in a nutshell, this kind of change management will require good leadership by the academics as well as local central government through focus group discussion to get the consensus in order for the kind of close the loop solution could be implemented. As for way forward, this is the takeaway. We need to understand the source of food waste generations. Hopefully, with the advent of IoT, Internet of Things, this review proposed by Wallace in the year 2017, with the advancement in IoT, the ICT, advanced management, the wish list is that if the waste volume and the location could be identified, this could better advise the treatment technology or allocation for technology selections, whether some of these waste can be channel for biogas productions or biorefinery or composting. As we know, database management is very crucial to enable mass balance modeling for nutrients recycling, for product quality assurance and formulations, for process integration to optimize energy usage, and to calculate the overall economic feasibility. In a nutshell, a lot of social economic impacts research can also be conducted with more comprehensive data collections. IoT can also be very useful to minimize the transportation route for the waste collections and transportations. Due to the high moisture contents in food waste, composting process could reduce the food waste volume up to 80%. And the end products are compost or leachate. Both can serve as organic soil amendment. In order to commercialize this product, it is essential to further characterize the nutrients in this product. This diagram shows a full and large-scale composting plant. Although the food waste may be collected from the restaurant or food industry, this waste stream will still contain a substantial amount of plastic or waste, which will require some mechanical pre-treatment. This waste stream will go through primary screening in order to filter out the oversized refuse, which will be sent to the landfill site. The screen material will be subjected to further composting process. Typically, at the industrial scale, this will take about 1 day. And further, after this process, after the composting, the product will be sent to the cure site. And this typically will take a few weeks to a few months, depending on the operating conditions, whether the compost are further treated by addition of microbial inoculant or thermal treatment. And finally, the product will still be screened to a more uniform particles. We call it the refined compost for further marketing. Another comprehensive review was conducted by Roy in this paper in year 2018. More research on composting is concerning about how the leachate could be better treated before being discharged to the environment. From the circular economic point of view, this leachate should be better treated to becoming the bioliquid fertilizer, as I mentioned before. However, this will require more stringent segregation at source to ensure the organic waste is not contaminated with heavy metal. I would like to highlight that productions of compost is not just to replace chemical fertilizers. Compost is not just NPK. A part of providing the macronutrient of NPK, compost typically also contain other micronutrients and humic acids, which will improve the physical property of the soil. And importantly, production of compost could offer more other co-benefits, such as supporting local food productions and reducing the greenhouse gases at the landfill site. A lot of research has been done to showcase the impact of compost or bioliquids application on soil to improve various properties of soil fertility. For example, in terms of physical property or chemical property, and also enrichment of microbial population in soil. Some of the research also reported the role of compost to remediate problematic soil or those which are polluted by heavy metals. As mentioned earlier, that characterizations of nutrient content in compost and bioliquid fertilizers are important to enhance the marketability of the compost product as well as the selling price. This is a field research site we established with a community located in Johor Bahru, involving 30 households who will segregate their food waste on daily basis. However, the food waste will be collected once a week with the design of a compost box equipped with dry leaf and soil to cover the daily food waste. For the past 2 years, we continuously monitor the nutrient content in the food waste, compost, and leachate. These figures nutrient content of NPK reported for leachate and compost in red color were analyzed by our team member. As you can see that there is a large variation of food waste compositions or nutrients as compared to other literature. This is largely due to variations of food waste compositions. This variation also emphasizes the importance of proper segregation of food waste based on different types. For example, if we could better know the percentage of meat or vegetable or different composition of food waste in the compost, we can better understand the nutrient range. Continuous research is needed to better understand this nutrient content in order to facilitate further product formulation. As a conclusion from this presentation, we have highlighted 4 major products that could be produced from food waste valorizations. Of course, our passion is to continuously promoting composting as a promising and viable technology to valorize food waste. And we like to emphasize that compost is not just to replace the chemical fertilizer. It is not just providing NPK to the crop, but it has more other value propositions such as improving soil structures and so on. We also like to emphasize the systemic closed-the-loop solution for food waste composting, ranging from the top-down approach to management of the upstream activities, emphasizing on the public-private partnership to build more large-scale composting facility which are viable. And as a researchers, we should focus more on product characterization, formulation, and quality control, especially in terms of pollutants minimization, such as heavy metal and so on. Equally important to close the loop will be the coordination with the local authority in charge of waste collection to finally application to agriculture land. This is typically can be a challenge because the local authority who in charge of waste collections, the department will be different from those department in charge of agriculture field. So in a nutshell, the role of academicians like us, experts, local government, the consensus building with multiple stakeholders are very crucial in order to enhance the coordination of the supply and demand change management. As for other technologies such as AD, biorefinery to produce biochemicals or biomaterials, we have witnessed, we have seen more than 2 to 3 folds of research publication over the past decades. However, most of these technology are still facing the challenges to address the economic feasibility. This is the conference we run each year in different cities in Asia. This year it was successfully conducted in Johor Bahru, UTM, the 7th International Conference on Low Carbon Asia and Beyond, with the theme Circular Economy Towards Sustainable Development. It was organized in last month. And for this year, we are able to secure 3 special issues, two journals, JERMA, Journal of Environmental Management and Energy, the Q1 journal, and also Chemical Engineering Transactions, the Scopus journal. We would like to cordially invite you to support the next series. Hopefully it will be conducted in Okayama, Japan. In the past, this conference has been successfully organized in Kuala Lumpur, Bangkok, Ho Chi Minh City, and Shanghai. Towards zero waste, leaving no one behind. We understand the complexity and challenges to close the loop for converting food waste to value-added products such as compost. Over the years, since 2017, through the UTM Green DNA Student Society, we have outreach a group of students to support a range of activity to realize this goal. From supporting the community composting plant in Johor to food waste composting demonstration in school, we continuously educate the public about the needs and urgency demand to segregate the food waste at source correctly and effectively, where the community can either compost at home, or they could also send the food waste to a community composting plant such as the one in Johor. Also, through the collaboration with UTM Low Carbon Asia Research Center, we have the opportunity to engage with local authority from Johor to Kuala Lumpur through FGD, focus group discussion, in order to enhance the consensus building and engage with multiple stakeholders. We hope that corporate and private sector who are interested in closing this loop could continue to communicate with us so that this goal can be realized. So please like us in Facebook. Most of this activity also conducted in collaboration with UTM Low Carbon Asia. Every year we run, as I mentioned, the Low Carbon Conference, summer school on green programs. And I like to end this slide with this famous Native American proverb. Hopefully each of us will play our role towards zero waste.